In our last chapter, in fact, when we first introduced derivatives, we basically said you would have a function d which would calculate the distance. And again, we did many different functions, but this was the very first one we talked about. We talked about the distance that an object travels could be found by plugging into a function. Let's call that function f of t. And that would tell you the total distance, let's say in feet, that object had traveled. Well, now what we did was we found the derivative, you'll recall, of that function, and that basically would give you the velocity. So the velocity would actually be equal to that derivative. And let's just say, for example, that you found the velocity, or the derivative, was a constant. Let's say that constant was 50. In other words, you found that car was moving at 50 feet per second. You could then plug that back into the original equation and determine at any point in time how far that car had moved. When we do integration, we're going to be applying this basic concept backwards. Let's assume that we have it graphically depicted. In other words, I'm going to give you the velocity, and from that we're just going to work backwards and come up with a formula for the distance. So what if I told you that the car was moving at 50 miles an hour, or 50 feet per second? The graph would merely be a horizontal line. If I wanted you to find how far that car had moved in the first 4 seconds, what would you do? From 0 to 4, graphically speaking, in 4 seconds, at 50 miles an hour, or 50 feet per second, the area underneath this curve would be equal to 200. Now think about the units on this as well. We're saying the car is going at 50 feet per second. Recall, when we had derivatives, these were always rates. And the same thing is going to be true here. I'm going to give you a rate. In this case, the car is moving at 50 feet per second. And then I gave you the number of seconds. Cancel. If it was 4 seconds, the car would move 50 times 4, or 200 feet. Now graphically it's pretty easy, but basically that's what we're going to be doing during this early part of this next chapter. During the early part of integration, I'm going to give you the rate at which something is traveling, and I will give you not always a time. There's other things that can be done here, but usually a time. At 50 feet per second, for 4 seconds, you would calculate 200 feet. Now, it's not always going to be this straightforward, and I'd like to do one of those examples right now. Let's assume that the velocity that the car was traveling at could be found by plugging into this formula, f of x, where x is equal to x squared plus 1. Graphically, my intercept would be right here at 1. And let's assume I want to know how far, by the way, the car traveled between the first and the 5th seconds. Graphically again, by the 5th second, the car would actually be going 26 feet per second. If I wish to know how far it went between the 1st and the 5th seconds, I need to find this area right here under my curve. Now that's not nearly as easy a calculation as the last one, where this was a constant. We will eventually learn how to take the integral, or how to integrate this function by using a definite integral to actually answer this question exactly. But I'd like to concentrate on it in the beginning here for how you would look at it graphically. So first of all, let's take a look at a chart of values. First of all, I am going to go by 2's. I am going to look at this middle chart. I'm going to still start at 1, but I'm going to make my change in x 2. So I'll start with 1, I'll proceed to 3, and then I'll proceed to 5. What would that look like graphically speaking? Well, my first value, when x was 1, was 2. And my second value, when x was 3, was 10. And what I've done is draw rectangles going from the left side to the right side. And then I started my second point and drew a rectangle going again from left to right. Now, notice that the area of this rectangle, it was too high because the value of that function here at 1 was 2, and the width was 2 because I went 2 units. Remember, my change in x was 2. So from 1 to 3 was 2, and it's too high. So the area of this rectangle would be 4. The area of the second rectangle, the value at 3, was 10. So this rectangle is 10 high, and again, too wide again, because my change in x is consistently always going to have to be the same, in this case 2. So 10 times 2 is 20. So the area of my rectangle was 24. Now notice when I use these values, there's some extra space left over here, and extra space left over above this rectangle. So this area is too low. When I did my left to right, or my left sums, these ended out to be too low. So this is the lower estimate. I know that the actual area underneath this curve would be more than 24. And again, I want to emphasize, if we can go back to the chart for just a moment, where those values came from. The first values were literally the first and second values on the chart. Notice I didn't use the last value. I didn't bother with the coordinates 5, 26. Let's look at the graph now to see why. When I got to the far right-hand side of my graph, remember, we're stopping here. There was no reason to continue drawing a rectangle in that direction, so I merely quit. Now, let's start with the right-hand side of my graph and work to the left. This time I will use that value. At 5, the value of my function was 26. And again, all my rectangles will be too wide. So 26 times 2 gives me an area of 52. My next value, I'll use 3, which is the same value, by the way, that I used on my last demonstration in yellow. And you'll notice as I go from right to left this time, I go 10 high, 2 wide, and 10 times 2 is 20. So this area I estimate to be 72. But notice this is too high. This time I'm including area that occurs above the graph. So I know that 72 is actually too much. But once again, I know the actual area is somewhere between my 72 and the 24 that I had earlier. What I need to do is take an average of those two. But before I do that, I would like to point out to you again where those numbers came from the charts that I created. When I started at 5, the value was 26. I used the value at 3, but notice I didn't bother to use the first value I had at 1. Again, if I look at the values from my chart, I used the 26 and the 10, but there was no reason to use my first value at 1. Again, I didn't have to go beyond the far left-hand side. Okay, let's go ahead and look at our final calculation now. I know that 24 was too small and 72 was too big. I basically want to split the difference and assume that literally, that line, or that curve in this case, actually splits the difference between these two so that the real answer is right in the middle. To find the median, or frankly the average in this case, I just take those two numbers, 24 plus 72, which is 96, divided by 2, and I get my average of those areas is 48. Now that's a pretty good estimate for what the real average underneath that curve is. But again, we used a delta x, or the change in my x was a 2. Let's go ahead and go beyond this now and assume that my delta x was 1. Let's take a look at our new chart when we do that. If I plug the values 1 through 5 directly into my chart, then the values I get are 2, 5, 10, 17, and 26. Again, I'm still using my basic function of y equals x squared plus 1. Let's take a look at what the graph looks like when I go by 1s instead of 2s. Now first of all, you'll notice here that there are my values I've plotted out: 1, 2, 2, 5, 3, 10, 4, 17, and 5, 26. Again, I went from left to right, so I used my value from 1, my value from 2, my value from 3, my value from 4, but did not use the value at 5. It's not necessary here again. So in this case, my values, or my difference in x, are I'm going by 1s. So I will literally just multiply my values this time by 1. So this is pretty easy, frankly. I'll just take 1 times 2 is 2, and 1 times 5 is 5, 1 times 10 is 10, and 1 times 17 is 17. So the areas of the rectangles came directly from my chart essentially this time, and I'll show you what I mean by that. Since I multiplied by 1, there were no changes in these values. But again, the sum of these rectangles will give me a low estimate. Again, there's still area left over above the rectangle between the rectangle and the curve. So I know the actual answer has to be more than 34. But again, what I wanted to emphasize to you here was where these numbers came from the chart. 2, 5, 10, and 17. Those were our left values. So basically, if I go back to my chart again, notice where I find 2, 5, 10, and 17. They're literally my first 4 values on the chart, and I could ignore the last one. Let's take a look now and see what happens as I go from right to left. As I start at 5, I will use the coordinate 26. When I start at 4, I will use 17, 3, 10, and 2, 5. Once again, there'll be no reason for me to use the first value from the chart because I'm not going to the right anymore. I stop right here. The area of this rectangle would be 1 times 26 is 26, 1 times 17 is 17, 1 times 10 is 10, and 1 times 5. So the sum of my rectangles this time would be 58. And again, just to emphasize this one more time, look where those numbers 5, 10, 17, and 26 came from right off my chart. Since I was actually multiplying by a delta x of 1 in this case, multiplying those by the width of the rectangle of 1 left those values completely intact. But the part I want you to see again is the left values became the first 4, and the right values became the last 4. In both cases, I left off literally one of the values from the chart. You'll notice this time too that the values that I got from the chart, or from the rectangles, excuse me, were more accurate. I got 34 and 58. The previous time, the values that I got were 72 and 24. Let's see what that does to my estimate. Originally, I knew the real number was somewhere between 24 and 72. That's a pretty wide spread, frankly. And I found that my estimate was 48. Now, it's not a terrible estimate, but I think we improved on it this time, because this time, if you look at my graphs, there was not quite as much waste in this version of the graph as there was in the earlier version. My rectangles, when they're narrower, when my delta x is smaller, conform more tightly to the graph, and therefore come up with a better estimate. This time, instead of thinking it's between 24 and 72, I have now confirmed that my real answer is somewhere between 34 and 58. It's a much tighter range of values that I have to deal with. This time, too, when I took the average to find the value between 34 and 58, I got a middle value of 46. So I got a much better estimate of what I think the real value is. I'm getting closer and closer. Finally, let's make delta x even smaller. Let's go back to my chart one more time, and instead of going by 1s, I'm going to go by halves. So I'll still start at 1, but then I'll do 1.5, 2, 2.5, 3, etc., all the way to 5. Let's take a look and see how these values translate to the graph. Now this time, you'll notice my area of waste is even smaller. The area of this rectangle, and there's going to be a whole lot more, I'm still going to go from left to right. So I started at 1. My value is 2. So the area of this rectangle is 2 times 1/2, or 1. My second one, the value is at 5. Excuse me, at 1.5, the value was 3.25. 3.25 times 1/2 would be 625, excuse me. And I can continue this. This value is 5 times 1/2 would be 2.5, etc., etc., etc. Now this time I have many more rectangles than I've had previously. In fact, I literally doubled it. Before I had 4 rectangles, I now have 8. And the sum of these rectangles is 39.5. Going from the right to the left, I will include the last value of my chart, which was 26 again, and then we'll back up to 4.5, 4, 3.5, etc., all the way down to ending with 1.5. And again, I will not use that last value for my chart. This time, the area of this rectangle would be 26 times 1/2 would actually be 13. Similarly, I take this value times 1/2 and I get the area of that rectangle, and the next, and the next, and the sum of all 8 rectangles this time would be 51.5. And let's take a look what happened to our values. Our original guess was 24 to 72. Our next range was 34 to 58. We're getting tighter and tighter. I actually made the lower bound 10 less, or excuse me, I raised it by 10, and the next time I actually lowered this one by 14, so I actually eliminated 24 values from my range. That's quite good. My next time I didn't eliminate quite so many, but you'll notice instead of from 34 to 58, it's from 39.5 to 51.5. Taking the average of those two numbers gives me an average of 45.5. Now you could continue this on and on and on and getting more and more and more accurate. Frankly, this is actually pretty close to the real answer. The real answer is 45.3 repeating. So I'm within 2/10 of the actual answer here. So I've gotten pretty accurate. If I continue on, it gets more and more accurate. And let's take a look at what we actually want to happen here. You can choose any delta x you want. And again, here's my graph. And I wanted to find the area between 1 and 5. In order to do that, I first went by 2's. I went from 1 to 3 and 3 to 5, and I got a better answer. I then went by 1's. I went from 1 to 2, 2 to 3, etc. And the next and final one I did was to go by halves, from 1 to 1.5, from 1.5 to 2, etc. What we want to have is the narrowest possible rectangle. As you make these rectangles more and more narrow, smaller and smaller, in pen you can't even visibly see the difference now between the rectangle and the curve. You want that to be so small that it's truly, literally, 0. What you want is to make these rectangles smaller and smaller and smaller in width until they really are practically 0. But here's the problem with doing it manually the way I've been doing it. We had a distance of 4 that we wished to cover. If you went by 2's, then my delta x, my change in x of 2, I had to have 2 rectangles in order to cover that distance of 4, where n was the number of rectangles and the delta x turned out to be the width of the rectangle. To cover the total distance of 4, I only had to use 2 rectangles. For the next one, I made my delta x only 1, and I needed 4 rectangles to cover that distance of 4. And when I used 1/2, I had to have 8. Well, let's say we even just went down to 1/1000 for the width. It would take 4,000 rectangles, and I still wouldn't have quite the exact answer. So what we're going to do is use calculus. What you want to do is use your basic area formula, which was f of x. And I'm going to put a little sub I on there to indicate I'm going to start with the first value and go all the way up to the last value, which would be n. Now, there is one difference here you need to know. The book is going to call the first value 0. And the last value, of course, as indicated here, would be n. Now, you take this number, the area, the height of the rectangle, would be multiplied times the width of the rectangle, which was your change in x. And if you took your height, your value from the chart, times your width, or how far you were changing x each time, you got the area of the rectangle. So what you want is the sum of all those rectangles beginning with I equals 0. So x sub 0 would be like the first value from your chart, all the way to I equals n, which would be the last value from your chart. But remember, when we went from the left side, we didn't use the last value on the chart. So we'll go one smaller. We'll go at n minus 1. And when you take all the sum of all those rectangles, you ended up with an estimate of the area. But remember, we want these triangles, or these rectangles, to be practically 0. The width of the rectangles to be practically 0. The number keeps accelerating larger and larger. By the time this gets down to almost 0, can you see that if this is approximately 0, that it would take literally infinity of these rectangles to fill that gap? So you literally think of this as the limit as n goes to infinity. And this would be your left Riemann sum by definition, or what I called the left sum, or in our cases, that was always the lower estimate. To do the right estimate, you do exactly the same thing. It's still width times length on those rectangles, but remember, we didn't use the first value. So instead of using the 0, I will start at the next value over, which is 1. And this time I do use the next value, so I go all the way up to n. So the right Riemann sum literally starts at 1 and goes all the way to n. But the thing I want you to see is you want the number of rectangles to literally go to infinity so that the width, or the change in x, literally goes to 0. And when you do that and calculate that, and we'll show you how to take a definite integral later, which does this method, you will have the exact answer for the area under the curve.